Okay, so we will start discussion on basic hydrodynamics. So, I will discuss incompressible Navier-Stokes today, and I will probably continue in the next set of lectures. So, I will cover these 4 topics. So, governing equations, then on vorticity, conservation laws, and illustrate using some examples. Okay, so, we will cover 4 small pieces, and I will try to illustrate basic ideas. So, we go to governing equations. Okay, so, I will brief you on basically Navier-Stokes equation. So, continuum approximation. So, I think I did mention about diffusion equation. So, there are molecules which were diffusing things, acting on like dust particles or diffusing heat, but we are looking at fluid approximation. I am looking at fluid, so fluid velocity. When I say wind is moving, so wind is not molecule which is moving, wind is gross or average state of set of molecules. So, it's typically I would say you can go up to millimeter packet size. So, this is some kind of a fluid element. I am not looking at molecules. So, an assumption is that my distance of interest or my length of interest L must be much bigger than mean free path length. Okay. So, our length scale should not be close to mean free path length, then I start seeing molecules, and I am not wanting to look at molecules. That description is different, that description is on kinetic theory, thermodynamics. So, that is not what is of interest for this course. This course is on fluid, and fluid has their own properties. These are I did mention for this diffusion equation that we need to consider the fluid motion for the movement of heat or for movement of particles. So, please keep in mind that we are interested in continuum approximation. Okay, then I am going to worry about incompressible flows. For this course, we are not going to go compressible flows, which are interesting on their own. Most of the astrophysics which Supratik does. So, this velocity is very fast. So, there are so sound speed is everybody knows. No? So, if sound speed, if the velocity of fluid is comparable to the sound speed, then we need to worry about density variations. So, we assume that our speeds are much lower than the sound speed. In fact, for me the sound speed is infinity. Okay. So, you can see from you can derive that sound speed is infinity. Okay. So, this equation is called continuity equation. Okay. This continuity equation. So, it's continuity of mass. Now, this is like if I have some mass here, then rate of change of mass inside this volume will be equal to the flux. No? So, from this you can derive this. So, again I will not get into the derivation of this equation, but this equation is basically conservation of mass. Now, we will assume that when the fluid is moving, so I can take any small fluid particle, a parcel, not particle, I will say parcel. Parcel I mean a packet which is millimeter size or bigger size, not too big, but yeah, this is intuitively called parcel. So, when the fluid is moving, we assume that the d rho by dt is 0. The density does not change on motion. So, that is a density locally could change, but when the fluid is moving, its density is not changing. So, just to also give, so if the fluid is here in this, and when it moves, its volume should not change, right? There are particles inside, and if all the particles are inside and it has a mass, if volume does not change, the density will not change. So, d rho by dt is 0 if the fluid on motion does not change its density. So, this is called incompressible approximation, this one d rho by dt is 0. So, let us see what does it imply. So, this is in fact is assumption of incompressibility. I cannot compress a fluid parcel, this is a packet. So, you can think of 1 centimeter cube fluid is going around, it is not changing its volume. So, let us start from here. Now, I will just do some basic vector calculus. In fact, we will need lot of vector calculus, but it will be basic ones. So, here I am going to expand this one, the second term, which will be what is the divergence of a scalar multiplied by vector. So, this is I want to make here rho del dot u plus u dot grad rho. This is this term, right. I mean, this you must have studied this divergence of a vector times scalar. Now, we have the first term is d rho by dt, this is equal to 0. Now, I can combine the first two terms, and what is this one? It is total time derivative of rho. Total means when I go with the fluid. So, this one is Eulerian local time derivative, I do not move with the fluid, but together is a I go with the fluid. So, this two term is d rho by dt, and the next one is rho del dot u is 0. Now, incompressible assumption implies that this is 0, this term is 0. So, what does it give you? Incompressible assumption implies, this assumption implies that rho del dot u is 0, but rho is positive number, rho is positive or not negative, rho is always positive number, that means del dot u is 0. So, this is my constraint. So, this is a constraint, this is not a equation for time advancing, this is a constraint on velocity. Okay. So, velocity must be satisfying this divergence free condition. So, this is called d free condition, d free condition. So, in this course we will only focus on incompressible fluid, though compressible fluids are also interesting and important. Now, somebody may say, well, why do you worry about incompressible fluid if it is such a constraining condition? It turns out for most fluid on the terrestrial environment, regular terrestrial environment, this is a very good assumption. So, what is the sound speed on for air, for example? So, you can everybody knows for room temperature and normal pressure is around 330 meters per second, right. So, 330 meters per second, the sound speed Cs for air, and for water the sound speed is around 1000 meters per second. Now, what is the speed typical in regular lab environment or even atmospheric environments? For air, atmospheric environment is 10 kilometer per hour, which will translate into 3 meters per second for atmospheric flows. So, it is much smaller than 330, right. So, the density variations are tiny, even though I can see that I cycle tube, I feel air, you know. So, air is compressible, but when it is moving the density variations are not large. For water, hardly I find a flow which is 1000 meters per second. So, incompressibility is very good assumption for many of the terrestrial applications, for atmosphere, for engineering flows, and even for like inside the earth. Yes, incompressibility is a good assumption. I mean, molten metals inside the earth which is not moving very fast. Okay. So, first thing you should do is this incompressible flows. Okay, is that clear? So, this is what we will stick ourselves to. So, I am going to say incompressible, and this is called Navier-Stokes equation. There are two people, Stokes is British and Navier is French. So, this given by these people. So, the form which we are going to use for this course is this form. So, I just want to mention that density is constant. So, strictly speaking, the density while in motion should be constant, but for if it is homogeneous fluid, you know, that means my things are not changing when I go from one position to other position on the average, then you can assume the density is constant everywhere. Okay, that is an assumption, but reasonable assumption. Okay, so that is what we will assume. So, in fact this is the rho is the density, which I will assume it to be constant, which is not strictly true. D rho by dt is 0 does not mean rho is constant, okay, is a total derivative, but fair enough. I mean, this is the detail which I will not discuss. So, this is the acceleration term, okay. This is the pressure gradient term. So, Newton's laws. So, this acceleration is force by mass. So, therefore, three forces, one is pressure gradient. So, as I said, so if there is a pressure difference between two surfaces, there will be a net force, and that is you can derive it. In fact, the best and cleanest description I find is in Landau's book, chapter 1. Okay. So, this is very nicely derived in pressure gradient. Viscous term is coming because of viscosity at two surfaces. So, we will assume this form. Okay. This is good for incompressible flows. This is reasonably good description, and this is the external force. Fu is external force, that could be gravity, it could be magnetic force, buoyancy is gravity, or rotation, or any other force. Okay. So, external force, not pressure or viscous, in addition to viscous and pressure. And as I said, incompressibility implies that we have this condition del dot U 0. Okay. So, at least for next set of lectures, this is what I am going to focus on. Okay. So, we need to also worry about non-dimensionalization. This plays a very critical role because we have to deal with systems of different sizes, different velocities, and it turns out we can map one system to other system. So, the example which we discussed in the last class was aeroplane, So, aeroplane, a big aeroplane and a small aeroplane has similar properties. In fact, we can map one to other if the Reynolds number is the same. There is a strict. So, in fact, I will show you how to map. Okay. So, we saw the equation in the last slide. So, I am going to make non-dimensional. So, by the way, non-dimensionalization will be of different types. So, what I will do today will not be same non-dimensionalization which I will do for Rayleigh-Benard convection. Okay. So, you have to choose your length scale according to convenience. So, today I am going to choose my length scale as equal to something similar to system size. So, one example is like aeroplane, or I can think of cylinder, flow past a cylinder, So, the velocity is going past a cylinder. So, this is very standard example in engineering, the flow past cylinder. So, what is the length scale for this problem? So, this diameter of the cylinder is a length scale. Okay. So, we choose that length scale as that diameter as my length scale. So, my position x, I am going to make x prime times L. So, what is the dimension of x prime? Is dimensionless, because x is centimeter and L is centimeter. So, x prime must have no dimension. What about velocity? What should I choose? U, which I am using. So, you can put a vector if you like. I am going to choose velocity scale. So, velocity would be far away from the cylinder, this is the mean velocity. I can write it here, mean velocity, far away velocity is streaming, which is a number. So, near the cylinder velocity is function of x and t, but far away from the cylinder I can say I am sending constant velocity. And so, we want a number, a single number. If you want, scale means you want to choose a number, single number for the whole system. So, u naught is my velocity scale. So, I multiply this by u prime. So, u prime and u are in the same direction, direction does not change, only the numbers have changed, and u prime is dimensionless, it has no dimension of centimeter per second or none of it. What about time? How do I get time? If I have dimension of length and dimension of velocity, then I can immediately construct dimension of time. So, what is the dimension of time, by the way? T will be L by u naught, straightforward. So, what should I write? T, which is dimension of seconds, or it could be hours, or it could be long time. Okay. But anyway, this T has a dimension. I multiply this by L by u naught, not multiply, I mean T equal to L by u naught times T prime. Similarly, you can define for pressure, external force. These are other two terms, right. So, if you saw the last equation, so we can also write down for that. So let us look at pressure. What is the dimension of pressure? So pressure was, so if I look at the last stuff, grad P. So let me do some rough work here. Grad P by rho was u dot, right. So pressure has, so P and rho look like similar. So pressure has dimension of u by T, and there is a length will go up and density, right. So from here you can see. So this will be rho u squared, L by T is u, so rho u squared. This is the dimension of pressure. So I can easily non-dimensionalize it. So I say P equal to rho, which is constant density, u naught square P prime. Okay. So you can play this game for all terms. In fact, it is very useful game. Non-dimensionalization is one of the important tools for fluid mechanics, plasma physics, and all fields actually. I mean, I would say that even quantum mechanics you can make non-dimensionalization. It helps life very much, especially for simulations. Okay. This is a separate matter, but we can play this game nicely.
So in this case, your rho is also 1, right?
So right now in this equation it is not 1, but I will choose it to be 1. For most of the future discussion after this, I will make rho is 1. Okay. So why carry a symbol, but for this one it is not 1. Okay. So let us look at few terms. I will not do for all terms, but I just want to do for few terms. So we have one term which is d, this term. I want to make it non-dimensional. So what do I do? Some of you know this very well, but I just want to do it for completeness. So u I am going to write as u naught u prime, and what about partial t? So this t del t t prime, correct. So this is one. So this term has dimension of, now I can replace this one t with u naught square by L partial u prime partial t prime. This is one term. I can look at the next term. So I will not do the all algebra. So u dot grad u becomes, so there are two u's, so that becomes u naught square, and grad will give you 1 by L del so u prime dot grad prime u prime. So I should say what is grad prime. So I can write it here now. I go back. So grad has dimension of length. So I should say grad is 1 by length. Sorry, grad is, so L grad prime. No, I made a mistake. This one. So grad has dimension of length. So grad prime will be dimensionless. Okay. So grad has dimension of length. I should multiply by L, that is grad prime. Okay, that's it. Okay, or divide by L. So either way. So L grad is grad prime. Okay. So if I just substitute this in Navier-Stokes equation, what will I get? I can take, look, interesting part is that both these acceleration terms have same prefactor in front, u naught square by L. So u naught square by L and del u prime dt prime, vectors, I must write the vectors, u prime dot prime u prime equal to, now I will not do all the algebra. So I will say u naught square by L, you can just show this. Now this I will tell as a homework problem, grad prime pre prime, this will cancel. So let us put the viscous term, and that I think I am going to do some rough work here. Nu grad square u, what will that be non-dimensionally? So nu has dimension of is velocity times length. So it is centimeter square per second or meter square per second. So nu I will just leave it nu 1 by L squared. I will not say nu prime, so nu is a parameter. So grad prime square u prime, and u prime will give u naught. So that is the term, nu u naught by L squared. So this term is nu u naught by L square grad prime square u prime. Okay. So, in this equation u naught square by L will cancel the first 3 terms. So, let us do this algebra for the last step dt prime plus u prime dot prime u prime equal to minus grad prime p prime plus, okay, rho has gone, rho is basically gone here. Now, there is a, okay, so this one rho it does not appear because I have replaced dynamic viscosity with kinematic viscosity. Now, we got, I have to divide this by u naught square by L, the last term. So, what will happen? One u naught will cancel, u naught, and one L will cancel, L.
Sir, for a particular problem, nu will be constant, right?
Yes. So, nu is a parameter for the problem.
For a particular problem, that will be constant.
Yes.
So, rho is also parameter
Yes, rho is a parameter.
for a particular.
Yeah, rho is a parameter. Yes. So, in this term, so I mean viscous term is nu grad square u is acceleration. This is dimension of acceleration. Okay, so I am equating acceleration. Now, what is this object? Does it have dimension or no? Inverse Reynolds number, and it is dimensionless. One way to check is the viscosity has dimension of velocity times length. So, velocity times length they will just cancel. So, I found a parameter which is non-dimensional. So, this term, the last term can be written as this one 1 by Reynolds number grad prime square u prime. So, this equation is dimensionless and we have one parameter instead of many parameters. So, in your original equation I had velocity u naught is a parameter, okay, which is not does not appear in the Navier-Stokes, but when I solve the problem u naught will be a parameter, length is a parameter, density is a parameter, nu is a parameter, but now I have only one parameter in the problem. And what is my velocity for this problem which is coming from the left? It is 1 unit, well, one non-dimensional unit. Okay. Now, so I will basically in computer we solve this equation, or in wind tunnel, actually wind tunnel is a slightly different game, but this is equation we want to solve in computer. Now, if I find pressure on this object or pressure gradient or let us say buoyancy, not buoyancy, lift to be some unit, okay, L, then how do I convert it to a real system? So, this problem gives me a lift, upward lift, for this problem it will be some number L. So, the real system I can always convert by my this transformation. So, real system, what is the dimension of well, lift has force, dimension of force is force density, well, we can let us say force density, lift per unit area or per unit volume also, okay, let us say lift. So, I will say rho times acceleration. So, I have some object like this, lift has in fact is a force. So, I have to multiply by this by volume. So, that will be L cube. So, I should not use the word lift, I should use a different pen, but yeah, so let us say lift. So, it has dimension. So, you want the lift, then force density has the dimension of force by volume. So, I have to multiply this by L cube. Now, I am getting in terms of rho primes and u primes. So, what do? I just multiply this by rho u naught L cube by T naught du prime by dt prime. So, the quantity which I need to multiply pre-factor is this one, rho u naught L cube by T naught. If I do it, then I will be able to compute lift on the real system. So, this is what is done in wind tunnels. So, wind tunnel you do obtain the number for one problem, then by appropriate scaling. So, you say, well, I make the length 10 times, velocity 3 times, then what will I by my lift? So, by keeping the same Reynolds number, you must keep, this equation requires that my Reynolds number must be the same, this equation. So, that is why our experiment must have the same Reynolds number, then only I can make connection, otherwise I cannot make connection. So, the experiment done in wind tunnel is for the same Reynolds number, but I can get the measurement of the lift on a small model, but then I can multiply with the appropriate ratios of lengths, ratios of velocities, I can compute lift on the real aeroplane and it will work. Okay, so, that is what is the importance of scaling. Now, scaling has one more advantage, well several more advantages, but I will tell you one more advantage in computer. So, suppose somebody wants to compute aeroplane is fine, but I want to compute for galaxy, I want to simulate galaxy. So, what is the length of a galaxy? Like is many light years. If I put in terms of centimeter, it is going to be huge, so like 10 power 30 centimeter or whatever, some number. Now, putting those numbers in computer is not a good idea. Putting large numbers, computers do not like. If I also do not like, I can't rig up 10 power 30. I remember order 1 numbers. So, something like 30 nobody remembers. Okay. So, this is not. So, in fact, why meter was chosen as a unit? It's simple, because human being height is 1 meter. So, that is why we choose 1 meter as our unit. Atomic physicists use angstrom as a unit. They do not choose meter as a unit, because they can't remember 10 power minus 9, 10 power minus 10 is a clumsy thing to do all the time. So, angstrom is their unit. Okay. So, similarly, you say, well, in computer you want to keep order 1. So, I want cylinder of size 1, that is what the computer likes, and you work with that. Okay. So, this is my equation for which I just wrote. So, this is the Reynolds number 1 by Reynolds number. Okay. So, in fact, I can also write as nu prime, non-dimensional viscosity if you like. So, this nu prime has no dimension. Okay. Inverse of Reynolds number is we can denote by nu prime, and other equation is very easy to see, that non-dimensional version is just nu prime grad dot that grad prime is 0. Of course, in future I will drop the primes, I will not keep prime, but most of the time we will assume that we are working with non-dimensional units, because it is convenient to work with them, and I can always go to real system by multiplying appropriately. Okay. So, this is called Reynolds number, this is the Reynolds number, and you can see one thing, that this is a nonlinear term. Okay. So, this is n lin, and what is this term? Is a viscous term, and this is a pressure gradient term. Pressure, my handwriting is not coming out well, is not very good, but is worse here.
It should be P prime, right?
P prime, you are right, thank you, is P prime, yes. So, pressure gradient. So, the nonlinear term of pressure gradient, what is the from this equation you can see that they are same order. U prime is order 1 at large scale. So, U prime, so I must make this remark, U prime will be multi scale, that means it will be different values at different scales, and there will be very tiny U prime as well. We will study that, in fact, what is velocity at different scale, but at large scale U prime is order 1. That is what I said, no, I mean U prime coming, in fact, U at from the left is coming as 1. So, U prime is order 1, grad is order 1. So, in fact, this is order 1, order 1. Is it everybody is agreeing to that? What about grad prime, P prime? That is also order 1, because grad is order 1, P prime is order 1. So, this is order 1. What about this term? This is also order 1. Okay. In fact, well, this where the okay. Now, so I think I will not. So, this part we will discuss a bit later. So, which is order 1? So, U prime at large scale. Okay. So, I will only make some loose remarks. At large scale, grad is order 1 and U prime is order 1. Okay. So, what happens to the ratio of n lin by viscous term, full viscous term? So, this is order 1 this inside inner bracket, okay, this inner bracket is order 1 and the order. So, the ratio will be nonlinear by n ln by full viscous is Reynolds number. Okay. So, the ratio of n linear term by viscous term at larger scale is Reynolds number. A small scale, of course, things we do not know what is grad prime behaving. Okay. So, that we will discuss that part later, but here this is a ratio, okay, n ln by viscous term is ratio. So, when system is very nonlinear, we say that this term, nonlinear term, this one dominates the viscous term, dominates the viscous term. So, large Reynolds number flows, we need to consider nonlinear term very much. If it is viscous flows, that means what is viscous flow, viscous term will dominate. So, that will be Reynolds number. So, let us see turbulent, I must write this here, turbulent flows Re much bigger than 1 and worry about n ln. N ln means nonlinear term, okay, n ln you are worried about nonlinear term. What about the viscous regime? Viscous regime nonlinear term is assumed to be small. So, n ln is much small compared to n ln, much small compared to viscous. So, what is the Reynolds number for this regime? Less than 1, much less than 1 or less than 1 is okay, or less than 1, it depends. So, it could be order 1, that is also called laminar, okay. So, order 1 is also called laminar.
Sir, how have you got this relation n ln by viscous equal to I?
Okay. So, you can see, so this n ln is from here, this box is order 1. So, I can let us look at this u dot u prime dot grad prime. Okay. Now, what is this one? 1 by Re, Re will go up, Re grad prime square u prime, right. This is a ratio, I just took the ratio of the two terms. Now, what is this term? U prime dot grad prime, how big is the term at large scales? 1, u prime is 1, grad prime is 1, right, because velocity I said is 1 unit. So, this is 1. What about this term? A large scale is also 1, grad prime is 1, u prime is 1. So, these two ratio is 1. So, what is left is Re. So, for turbulent regime Re is much bigger than 1 and we need to worry about n ln term. For viscous regime n ln, if it is Reynolds number order 1, then you both are comparable. If it is much less than 1, then just worry about viscous. And there are times when you just worry about viscous, in fact you set viscous linear n ln term to 0, okay, there is also a case which, but we will mostly focus on the turbulent regime. I will do some instability analysis where we will keep the viscous term, this term, but we will basically focus mostly on Reynolds number much greater than 1. This is turbulence course, so we need to worry about n ln term. Okay. So, in tensor notation, so this is also very important notation which I will need it for this course. So, I is a index. So, velocity you write as u, we normally write as ux, ui, uz, but instead of that you write ui and I goes from 1 to 3. 1 is x, 2 is y and z, 3 is z. So, the nonlinear term for incompressible flows will look like this. In fact, I will just show you very easily. So, nonlinear term, what was it? U dot grad u, right. So, this is u, so this ux del x u, right. So, this is, let us write this ux dx u vector plus uy del y u vector plus uz del z u vector. In terms of tensor notation, I am looking at x component or y component or z component. So, I will put I. So, instead of writing vector u, I will just replace this by I. This is true for all, either x or y or z. So, that is the beauty of this notation. We do not need to write x particularly or y or z, just say I. If you want x, then put I equal to 1, y 2, z 3. So, and what is us partial x? These 3 I can write as uj del j. Now, there is a implicit assumption that it is summed. So, the Einstein, this was first invented by Einstein, at least is attributed to Einstein. So, if I write a repeated index, that means it is summed, and this is ui. Okay. So, it is implicitly assumed that this is summed over j. J will not, this is only function of I, but it is not function of j. If there is a repeated index, that is always summed. Okay. So, we do not write this sum, in fact this is equivalent to uj del j ui. Okay. Now, our incompressible condition, what does it tell you? It tells you that this is incompressible condition is ui del I ui is 0. Of course, this is assumption that there is a sum. So, del x ux plus del y ui plus del z uz is 0. So, I can use this to simplify this one, in fact write it in a more compact notation. So, let us look at now this term. Okay. This is what I want to do discuss. So, let us make a box here, del j uj ui. Now, derivative is acting on the product. So, I can use product rule. So, what will that be? uj del j ui plus ui del j uj, correct, is a product rule. Of course, you please remember that I am had to sum over j's. Now, what is this term? 0. So, this term goes away, and this is nothing but uj del j ui, which is same as what I have it here. These two terms are same. So, instead of writing as u dot grad u, is very convenient many times to write that as a partial j uj ui. Okay. Especially for conservation laws, which I am going to do a bit later, this one is very important notation. The pressure gradient is this one, right, along I direction. So, this is along I direction, and this is the force along I direction, and this is a viscous term along I direction. Now, I said del j, this 2 j's means del x square plus del y square plus del z square, which is Laplacian. So, this is a tensor notation which is very useful, especially for conservation laws and some of these derivations. Okay. So, what about pressure in incompressible flows? It is a very important step. So, pressure I can compute from given velocity. Okay. Pressure I can easily compute. How will I do it? So, this is my Navier-Stokes equation, right. So, this is a vector equation. So, I can take u vector dot. So, what happens to many terms? What about the first term? So, it is a d by dt u dot u. So, in fact no, sorry, I made a mistake. No, I do not take dot, divergence, I am sorry, divergence. Take a divergence of this, take a divergence of this equation. So, what happens to the first term? 0, right. So, this term is gone. What about this term? Laplacian pressure. So, this is minus Laplacian, it becomes Laplacian p. I will assume that, well, let us keep this del dot fu, not, let us not assume anything. So, this is maybe divergence free. This term I will, you can prove it easily that this term is also 0, so Laplacian and divergence commute. Okay, you can push divergence. So, this you can also see in terms of notation. So, this term also goes to 0. Now, this is divergence of the nonlinear term, I will call n. So, in fact, this is a notation I will use in later part of the course. This is a nonlinear term n vector. So, this is what we got. Okay. So, I can rewrite this as Laplacian p equal to divergence of this is going to the right hand side minus n plus Fu, and n is function only of u vector, no. So, this is known, given the velocity field, this one is known to me, and force is also known to me, somebody will give me the force. So, the right hand side is known, this whole thing is, I can compute divergence if the fields are known. Okay. So, I can, so now what is this equation? This is a standard equation in mathematical physics, this is called Poisson equation. So, this is unknown, this is unknown. So, Laplacian of unknown equal to some source term, this we can call it source term, is a scalar source. So, I can compute pressure given the boundary condition. So, my source is known, give me the boundary condition, I can compute force, I can compute the unknown which is P. So, P can be computed, in fact is written as Laplacian minus 2 of the source. In fact, this is exactly same what you do for in electrostatics. So, given the charge density, I can compute potential, right, that is what is done in so this is what is done in electrostatics or magnetostatics. This is one of the standard equation which is very useful equation. Okay. So, this is highly used in electrodynamics and also in fluid mechanics. So, pressure will be in incompressible fluid, pressure is not an independent variable, pressure is a dependent variable, this is a dependent variable, depends on what? Depends on velocity field and force field, it is a dependent variable. Okay. So, we will compute pressure by this trick. Now, I also need this definition for my future derivation. So, this material derivative which I did discuss a while ago, this is called total derivative. If I move with the fluid, then how f changes is function of time. So, this is total derivative df dt is partial derivative plus material derivative, right. I mean the proof is easy. So, f is function of x vector in t. So, df dt plus df dx dx dt, and similarly for y, all three components. So, this is dx by dt is velocity, we are moving with the fluid. So, this will give you what I got above, no, not rho, this is f. So, df, this is true for, so this is u dot grad f. So, f could be also vector or f could be scalar. So, f could be energy, f could be u squared, f could be in fact magnetic field, or f could be velocity field itself. Okay. So, this ends my first part which is basic equations. So, I will close now. Thank you.